So here we have a simplified quantum dot polymer device, just one of multiple different architectures that you could have. Here we have the cathode at the top, which is where electrons would be attracted to because the cathode is positive. The anode is negative, so that's going to have an attraction for the holes. We usually have a layer here that's hole only transport so that we block any electrons that could possibly get through. And in the middle we have a layer here where it's a composite polymer and quantum dots. So we have quantum dots mixed up in a polymer, and then you spread it on top of the anode, and then you put the cathode down on top of that. The polymer generally in this case could be like a P3HT or a couple of other things, TPD. It will conduct holes. It will allow the holes to be conducted to the anode, and the quantum dots will conduct electrons. Down here is an energy level diagram, so you can see as energy increases, we have the polymer. The band gap here for the polymer is slightly higher overall than the band gap for the quantum dots. What this means is that when light shines on this, we can either create charge carriers in the quantum dot or in the polymer, but in this case, for the sake of just showing you how what's going on, I'm going to create those charge carriers in the polymer. So light comes in, it moves an electron up to the conduction band of the polymer. Now this electron is going to be attracted to the cathode, and the hole is going to be attracted to the anode. So they're going to move together as an exciton pair, and then the electron is going to have to jump from the polymer to the quantum dot. Then now that they're separated from each other, they'll be attracted to their respective anode and cathode, and then they have to hop again from that material to the anode and the cathode. So we have 5 steps here. We're going to form an exciton. That's going to migrate to the interface between the two, and then those charges are going to have to separate from each other. The electron has to hop from one material to the other, and then once those charges have been transported to the anode and the cathode, then those charge carriers have to jump again to the anode or to the cathode. Each one of those interfaces, whether that's jumping from quantum dot to quantum dot to quantum dot to get to the cathode, or polymer molecule to polymer molecule to get to the anode, either way, there are interfaces between each one of these pieces, and the electron has to hop from one to the other. Now, if there's a small potential barrier, then this might happen via tunneling. I have another quick example. Here's some quantum dots inside a polymer host. If I excite a charge pair, an electron to the conduction band inside one quantum dot, then I can separate those, but each one of those charge carriers has to jump from one material to the next.